Chapter 15. Ice and Rain. Protection. Ice control systems. Rain, snow and ice are transportation's long-time enemies. Flying has added a new dimension, particularly with respect to ice. Under certain atmospheric conditions, ice can build rapidly on airfoils and air inlets. On days when there is visible moisture in the air, ice can form on aircraft leading edge surfaces at altitudes where freezing temperatures start. Water droplets in the air can be supercooled to below freezing without actually turning into ice unless they are disturbed in some manner. This unusual occurrence is partly due to the surface tension of the water droplet not allowing the droplet to expand and freeze. However, when aircraft surfaces disturb these droplets, they immediately turn to ice on the aircraft surfaces. The two types of ice encountered during flight are clear and rime. Clear ice forms when the remaining liquid portion of the water drop flows out over the aircraft's surface, gradually freezing as a smooth sheet of solid ice. Formation occurs when droplets are large, such as in rain or in cumuliform clouds. Clear ice is hard, heavy, and tenacious. Its removal by de-icing equipment is especially difficult. Rime ice forms when water drops are small, such as those in stratified clouds or light drizzle. The liquid portion remaining after initial impact freezes rapidly before the drop has time to spread over the aircraft surface. The small frozen droplets trap air, giving the ice a white appearance. Rime ice is lighter in weight than clear ice, and its weight is of little significance. However, its irregular shape and rough surface decrease the effectiveness of the aerodynamic efficiency of airfoils, reducing lift and increasing drag. Rime ice is brittle and more easily removed than clear ice. Mixed clear and rime icing can form rapidly when water drops vary in size or when liquid drops intermingle with snow or ice particles. Ice particles become embedded in clear ice, building a very rough accumulation, sometimes in a mushroom shape on leading edges. Ice may be expected to form whenever there is visible moisture in the air and temperature is near or below freezing. An exception is carburetor icing, which can occur during warm weather with no visible moisture present. Ice or frost forming on aircraft creates two basic hazards: the resulting malformation of the airfoil that could decrease the amount of lift, the additional weight and unequal formation of the ice that could cause unbalancing of the aircraft, making it hard to control. Enough ice to cause an unsafe flight condition can form in a very short period of time. Thus, some method of ice prevention or removal is necessary. Figure 151 shows the effects of ice on a leading edge. Icing effects. Ice buildup increases drag and reduces lift. It causes destructive vibration and hampers true instrument readings. Control surfaces become unbalanced or frozen. Fixed slots are filled and movable slots jammed. Radio reception is hampered and engine performance is affected. Ice, snow and slush have a direct impact on the safety of flight, not only because of degraded lift, reduced takeoff performance and/or maneuverability of the aircraft, but when chunks break off, they can also cause engine failures and structural damage. Fuselage aft-mounted engines are particularly susceptible to this foreign object damage (FOD) phenomenon. Wing-mounted engines are not excluded, however. Ice can be present on any part of the aircraft, and when it breaks off, there is some probability that it could go into an engine. The worst case is that ice on the wing breaks off during takeoff due to the flexing of the wing and goes directly into the engine, leading to surge, vibration, and complete thrust loss. Light snow that is loose on the wing surfaces and the fuselage can also cause engine damage, leading to surge, vibration, and thrust loss. Whenever icing conditions are encountered, the performance characteristics of the airplane deteriorate. Figure 152. Increased aerodynamic drag increases fuel consumption, reducing the airplane's range and making it more difficult to maintain speed. Decreased rate of climb must be anticipated, not only because of the decrease in wing and empennage efficiency, but also because of the possible reduced efficiency of the propellers and increase in gross weight. Abrupt maneuvering and steep turns at low speeds must be avoided because the airplane stalls at higher than published speeds with ice accumulation. On final approach for landing, increased airspeed must be maintained to compensate for this increased stall speed. After touchdown with heavy ice accumulation, landing distances may be as much as twice the normal distance due to the increased landing speeds. In this chapter, ice prevention and ice elimination using pneumatic pressure, application of heat, and the application of fluid is discussed. The ice and rain protection systems used on aircraft keep ice from forming on the following airplane components: wing leading edges, horizontal and vertical stabilizer leading edges, engine cowl leading edges, propellers, propeller spinner, air data probes, flight deck windows, water and waste system lines and drains, antenna. Figure 153 gives an overview of ice and rain protection systems installed in a large transport category aircraft. In modern aircraft, many of these systems are automatically controlled by the ice detection system and onboard computers. Ice detector system. Ice can be detected visually, but most modern aircraft have one or more ice detector sensors that warn the flight crew of icing conditions. An annunciator light comes on to alert the flight crew. In some aircraft models, multiple ice detectors are used, and the ice detection system automatically turns on the WAI systems when icing is detected. Figure 154. Ice prevention. Several means to prevent or control ice formation are used in aircraft today. Heating surfaces with hot air, heating by electrical elements, breaking up ice formations, usually by inflatable boots, chemical application. Equipment is designed for anti-icing or for de-icing. Anti-icing equipment is turned on before entering icing conditions and is designed to prevent ice from forming. A surface may be anti-iced by keeping it dry, by heating to a temperature that evaporates water upon impingement, or by heating the surface just enough to prevent freezing, maintaining it running wet. De-icing equipment is designed to remove ice after it begins to accumulate, typically on the wings and stabilizer leading edges. Ice may be controlled on aircraft structure by the methods described in Figure 155. Wing and stabilizer anti-icing systems. The wing leading edges, or leading edge slats, and horizontal and vertical stabilizer leading edges of many aircraft, make and models have anti-icing systems installed to prevent the formation of ice on these components. The most common anti-icing systems used are thermal pneumatic, thermal electric, and chemical. Most general aviation GA aircraft equipped to fly in icing conditions use pneumatic de-icing boots or a chemical anti-ice system. High-performance aircraft may have weeping wings. Large transport category aircraft are equipped with advanced thermal pneumatic or thermal electric anti-icing systems that are controlled automatically to prevent the formation of ice. Thermal pneumatic anti-icing. Thermal systems used for the purpose of preventing the formation of ice or for de-icing airfoil leading edges usually use heated air ducted spanwise along the inside of the leading edge of the airfoil and distributed around its inner surface. These thermal pneumatic anti-icing systems are used for wings, leading edge slats, horizontal and vertical stabilizers, engine inlets, and more. There are several sources of heated air, including hot bleed air from the turbine compressor, engine exhaust heat exchangers, and ram air heated by a combustion heater. Wing anti-ice. WAI system. Thermal Wing Anti-Ice, WAI or TAI, systems for business jet and large transport category aircraft typically use hot air bled from the engine compressor, figure 156. Relatively large amounts of very hot air can be bled off the compressor, providing a satisfactory source of anti-icing heat. The hot air is routed through ducting, manifolds and valves to components that need to be anti-iced. Figure 157 shows a typical WAI system schematic for a business jet. The bleed air is routed to each wing leading edge by an ejector in each wing inboard area. The ejector discharges the bleed air into piccolo tubes for distribution along the leading edge. Fresh, ambient air is introduced into the wing leading edge by two flush-mounted ram air scoops in each wing leading edge, one at the wing root and one near the wingtip. The ejectors entrain ambient air, reduce the temperature of the bleed air. Leading edge slat anti-ice system. Aircraft that utilize leading edge slats often use bleed air from the engine compressor to prevent the formation of frost on these surfaces. On a modern transport category aircraft, the pneumatic system supplies bleed air for this purpose. WAI valves control the airflow from the pneumatic system to WAI ducts. The WAI ducts carry the air to the slats. Holes in the bottom of each slat let the air out. The airfoil and cowl ice protection system, ACIPS computer card, controls the WAI valves, and pressure sensors send duct air pressure data to the computer. The aircrew can select an auto or manual mode with the WAI selector. In the auto mode, the system turns on when the ice detection system detects ice. The off and on positions are used for manual control of the WAI system. The WAI system is only used in the air, except for ground tests. The weight on wheel system and/or airspeed data disarms the system when the aircraft is on the ground. Figure 159. WAI valve. The WAI valve controls the flow of bleed air from the pneumatic system to the WAI ducts. The valve is electrically controlled and pneumatically actuated. The torque motor controls operation of the valve. With no electrical power to the torque motor, air pressure on one side of the actuator holds the valve closed. Electrical current through the torque motor allows air pressure to open the valve. As the torque motor current increases, the valve opening increases. Figure 1510. Y pressure sensor. The WAI pressure sensor senses the air pressure in the WAI duct after the WAI valve. The ACIPS computer card uses the pressure information to control the WAI system. Y ducts. The WAI ducts move air from the pneumatic system through the wing leading edge to the leading edge slats. Figure 159 shows that only leading edge slat sections 3, 4 and 5 on the left wing and 10, 11 and 12 on the right wing receive bleed air for WAI. Sections of the WAI ducting are perforated. The holes allow air to flow into the space inside the leading edge slats. The air leaves the slats through holes in the bottom of each slat. Some WAI ducts have connecting T-ducts that telescope to direct air into the slats while extended. The telescoping section attached to the slat on one end slides over the narrow diameter T-section that is connected into the WAI duct. A seal prevents any loss of air. This arrangement allows warm air delivery to the slats while retracted, in transit, and fully deployed. Figure 1511. WAI control system. Modern aircraft use several onboard computers to control aircraft systems. The WAI system is controlled by the ACIPS computer card. The ACIPS computer card controls both WAI valves. The required positions of the WAI valves change as bleed air temperature and altitude change. The left and right valves operate at the same time to heat both wings equally. This keeps the airplane aerodynamically stable in icing conditions. The WAI pressure sensors supply feedback information to the WAIAC IPS computer card for WAI valve control and position indication. If either pressure sensor fails, the WAIAC IPS computer card sets the related WAI valve to either fully open or fully closed. If either valve fails closed, the WAI computer card keeps the other valve closed. WAI indication system. The aircrew can monitor the WAI system on the onboard computer maintenance page. Figure 1513. The following information is shown: wing manifold press, pneumatic duct pressure in pounds per square inch gauge. Y system. Built-in test equipment, BITE test. Byte circuits in the WAIAC IPS computer card continuously monitor the WAI system. Faults that affect the dispatch of the aircraft cause status messages. Other faults cause Central Maintenance Computer System, CMCS, maintenance messages. The byte in the WAI AKIPS computer card also performs automatic power-up and periodic tests. Faults found during these tests that affect dispatch cause status messages. Other faults cause CMCS maintenance messages. The power-up test occurs when the card gets power. Byte does a test of the card hardware and software functions and the valve and pressure sensor interfaces. The valves do not move during this test. The periodic test occurs when all these conditions are true. The airplane has been on the ground between 1 and 5 minutes. The WAI selector is set to auto or on. Air-driven hydraulic pumps are not in intermittent operation. Bleed pressure is sufficient to open the WAI valves. The time since the last periodic test is more than 24 hours. During this test, the WAI valves cycle open and closed. This test makes sure that valve malfunctions are detected. Thermal electric anti-icing. Electricity is used to heat various components on an aircraft so that ice does not form. This type of anti-ice is typically limited to small components due to high amperage draw. Effective thermal electric anti-ice is used on most air data probes, such as pitot tubes, static airports, TAT and AOA probes, ice detectors, and engine P2/T2 sensors. Water lines, wastewater drains, and some turboprop inlet cowls are also heated with electricity to prevent ice from forming. Transport category and high-performance aircraft use thermal electric anti-icing in windshields. In devices that use thermal electric anti-ice, current flows through an integral conductive element that produces heat. The temperature of the component is elevated above the freezing point of water, so ice cannot form. Various schemes are used, such as an internal coil wire, externally wrapped blankets or tapes, as well as conductive films and heated gaskets. A basic discussion of probe heat follows. Windshield heat and portable water heat anti-ice are discussed later in this chapter. Propeller dice boots, which also are used for anti-ice, are also thermal electric and discussed in this chapter. Data probes that protrude into the ambient airstream are particularly susceptible to ice formation in flight. Figure 1514 illustrates the types and location probes that use thermal electric heat on one airliner. A pitot tube, for example, contains an internal electric element that is controlled by a switch in the flight deck. Use caution checking the function of the pitot heat when the aircraft is on the ground. The tube gets extremely hot since it must keep ice from forming at altitude in temperatures near 50 degrees Fahrenheit at speeds possibly over 500 miles per hour. An ammeter or load meter in the circuit can be used to safely determine functionality. Simple probe heat circuits exist on GA aircraft with a switch and a circuit breaker to activate and protect the device. Advanced aircraft may have more complex circuitry in which control is by computer, and flight condition of the aircraft is considered before thermal electric heaters are activated automatically. Figure 1515 shows such a circuit for a pitot tube. The primary flight computer, PFC, supplies signals for the Air Data Card, ADC, to energize ground and air heat control relays to activate probe heat. Information concerning speed of the aircraft, whether it is in the air or on the ground, and if the engines are running, are factors considered by the ADC logic. Similar controls are used for other probe heaters. Chemical anti-icing. Chemical anti-icing is used in some aircraft to anti-ice the leading edges of the wing, stabilizers, windshields, and propellers. The wing and stabilizer systems are often called weeping wing systems, or are known by their trade name of wing and stabilizer deicing systems. GA aircraft and turboprop commuter-type aircraft often use a pneumatic deicing system to break off ice after it has formed. Sources of operating air. The source of operating air for DEIS boot systems varies with the type of power plant installed on the aircraft. Reciprocating engine aircraft typically use a dedicated engine-driven air pump mounted on the accessory drive gearbox of the engine. The suction side of the pump is used to operate the gyroscopic instruments installed on the aircraft. It is also used to hold the DEIS boots tight to the aircraft when they are not inflated. The pressure side of the pump supplies air to inflate the DEIS boots, which breaks up ice that has formed on the wing and stabilizer leading edges. The pump operates continuously. Valves, regulators and switches in the flight deck are used to control the flow of source air to the system. Turbine engine bleed air. The source of DEIS boot operating air on turbine engine aircraft is typically bleed air from the engine compressors. A relatively low volume of air on an intermittent basis is required to operate the boots. This has little effect on engine power, enabling use of bleed air instead of adding a separate engine-driven air pump. Valves controlled by switches in the flight deck deliver air to the boots when requested. Pneumatic DEIS boot system for general aviation aircraft. GA aircraft, especially twin-engine models, are commonly equipped with pneumatic DEISer systems. Rubber boots are attached with glue to the leading edges of the wings and stabilizers. These boots have a series of inflatable tubes. During operation, the tubes are inflated and deflated in an alternating cycle. Figure 1517. This inflation and deflation causes the ice to crack and break off. The ice is then carried away by the airstream. Boots used in GA aircraft typically inflate and deflate along the length of the wing. In larger turboprop aircraft, the boots are installed in sections along the wing, with the different sections operating alternately and symmetrically about the fuselage. This is done so that any disturbance to airflow caused by an inflated tube is kept to a minimum by inflating only short sections on each wing at a time. GA system operation. Figure 1518 shows a DEIS system used on a GA twin-engine aircraft with reciprocating engines. In normal flight, all of the components in the DEIS system are de-energized. Discharge air from the dry air pumps is dumped overboard through the DEIS control valves. The deflate valve is open, connecting the DEIS boots to the suction side of the pump through the check valve manifold and the vacuum regulator. The gyroscopic instruments are also connected to the vacuum side of the dry air pump. The vacuum regulator is set to supply the optimum suction for the gyros, which is sufficient to hold the boots tightly against the airfoil surfaces. When the switch shown in figure 1519 is pushed on, the solenoid-operated DEIS control valves in each nacelle open and the deflate valve energizes and closes. Pressurized air from the discharge side of the pumps is routed through the control valves to the DEIS boot. When the system reaches 17 psi, pressure switches located on the deflate valve de-energize the DEIS control valve solenoids. The valves close and route pump air output overboard. The deflate valve opens and the boots are again connected to vacuum. On this simple system, the pilot must manually start this inflation-deflation cycle by pushing the switch each time DEIS is required. Larger aircraft with more complex systems may include a timer, which will cycle the system automatically until turned off. The use of distributor valves is also common. A distributor valve is a multi-position control valve controlled by the timer. It routes air to different DEIS boots in a sequence that minimizes aerodynamic disturbances as the ice breaks of the aircraft. Boots are inflated symmetrically on each side of the fuselage to maintain control in flight while DEISing occurs. Distributor valves are solenoid-operated and incorporate the deflate valve function to reconnect the DEIS boots with the vacuum side of the pump after all have been inflated. Combining functional components of a DEIS system into a single unit is fairly common. Figure 1520 illustrates the right side of a large aircraft DEIS boot system. The left side is the same. In addition to the distributor valves, which combine functions of a control valve and deflate valve, the system also uses a combination unit. This unit combines the functions of a shutoff control valve for all pump supply air, as well as a pressure regulator for the system. It also contains a secondary air filter. DEIS system for turboprop aircraft. Figure 1521 shows a pneumatic DEIS system used on a turboprop aircraft. The source of pneumatic air is engine bleed air, which is used to inflate 2 inboard wing boots, 2 outboard boots, and horizontal stabilizer boots. Additional bleed air is routed through the brake DEIS valve to the brakes. A 3-position switch controls the operation of the boots. This switch is spring-loaded to the center off position. When ice has accumulated, the switch should be selected to the single cycle up position and released. Figure 1.522. Pressure-regulated bleed air from the engine compressors supply air through bleed airflow control units and pneumatic shutoff valves to a pneumatic control assembly that inflates the wing boots. After an inflation period of 6 seconds, an electronic timer switches the distributor in the control assembly to deflate the wing boots, and a 4-second inflation begins in the horizontal stabilizer boots. After these boots have been inflated and deflated, the cycle is complete, and all boots are again held down tightly against the wings and horizontal stabilizer by vacuum. The spring-loaded switch must be selected up again for another cycle to occur. Each engine supplies a common bleed air manifold. To ensure the operation of the system, if one engine is inoperative, a flow control unit with check valve is incorporated in the bleed air line from each engine to prevent the loss of pressure through the compressor of the inoperative engine. If the boots fail to function sequentially, they may be operated manually by selecting the down position of the same DEIS cycle switch. Depressing and holding it in the manual. Down position inflates all the boots simultaneously. When the switch is released, it returns to the spring-loaded off position, and each boot is deflated and held by vacuum. When operated manually, the boot should not be left inflated for more than 7 to 10 seconds, as a new layer of ice may begin to form on the expanded boots and become unremovable. If one engine is inoperative, the loss of its pneumatic pressure does not affect boot operation. Electric power to the boot system is required to inflate the boots in either single cycle or manual operation. When electric power is lost, the vacuum holds the boots tightly against the leading edge. DEISing system components. Several components are used to construct all DEIS boot systems. The components may differ slightly in name and location within the system, depending on the aircraft. Components may also combine functions to save space and weight. The basic functions of filtering, pressure regulation, distribution, and attachment to a vacuum when boots are not in use must all be present. Check valves must also be installed to prevent backflow in the system. Manifolds are common on multi-engine aircraft to allow sourcing of low-pressure air from both engine pumps. Note that air pump pressure is typically expelled overboard when not needed. Bleed air is shut off by a valve when not needed for dice boot operation on turbine engine aircraft. A timer or control unit with an automatic mode exists on many aircraft to repeat the DEIS cycle periodically. Wet-type engine-driven air pump. To provide pressure for the DEIS boots, older aircraft may use a wet-type engine-driven air pump mounted on the accessory drive gear case of the engine. Some modern aircraft may also use a wet-type air pump because of its durability. The pump is typically a 4-vane, positive displacement pump. Engine oil passes from the accessory case through the pump mounting base flange to lubricate the pump. Some of the oil is entrained in the output air and must be removed by an oil separator before it is sent through other components in the DEIS system. When installing a wet-type pump, care should be taken to ensure that the oil passage in the gasket, pump, and mounting flange are aligned to ensure lubrication. Figure 1523. Dry-type engine-driven air pump. Most modern GA aircraft are equipped with a dry-type engine-driven air pump. It is also mounted on the engine accessory drive case. However, it is not lubricated with engine oil. The pump is constructed with carbon rotor vanes and bearings. The carbon material wears at a controlled rate to provide adequate lubrication without the need for oil. This keeps output air oil free. Thus, the use of an oil separator is not required. Caution should be used to prevent oil, grease, or degreasing fluids from entering the pump or the air system to ensure proper pump and system operation. Figure 1524. Dry-type and wet-type pumps are virtually maintenance-free. Mounting bolts should be checked for security, as should all hose connections. Wet-type pumps have a longer time before requiring overhaul, but dry-type pumps give the assurance that the DEIS system will not be contaminated with oil. Oil separator. An oil separator is required for each wet-type air pump. Pump output air flows through the separator where most of the oil is removed and sent back to the engine through a drain line. Some systems may include a secondary separator to ensure oil-free air is delivered to the DEIS system. There are no moving parts in an oil separator. A convoluted, coiled or twisted interior allows the air to pass, while the oil condenses and drains back to the engine. The only maintenance required on the separator is flushing the interior of the unit with a specified solvent. This should be done at intervals prescribed in the applicable maintenance manual. Figure 1525. Control valve. A control valve is a solenoid-operated valve that allows air from the pump to enter the DEIS system. When energized by the DEIS switch in the flight deck, the valve opens. The control valve dumps pump air overboard when the DEIS system is not in use. Many control valves are built in combination with pressure relief valves that keeps the DEIS system safe from overpressure. Figure 1526. Deflate valve. All DEIS boot systems require a means for connecting vacuum from the air pump to the boots when the boots are not in use. This ensures the boots are held tightly deflated against the aircraft structure to provide the significant change in size and shape needed to break off accumulated ice when the boots inflate. One single deflate valve is used on simple DEIS boot systems. The deflate valve is solenoid operated. It is located at a point in the system where, when closed, air is delivered to the boots. When open, vacuum is applied. Often, The deflate function is built into another unit, such as a distributor valve discussed next. Distributor valve. A distributor valve is a type of control valve used in relatively complex dice boot systems. It is an electrically operated solenoid valve controlled by the dice boot system timer. Timer/control unit. All but the simplest of dice systems contain a timer or control unit. This device controls the action of the distributor valve to ensure all boots are inflated in the proper sequence and for the correct duration. 6 seconds of inflation is common to break off accumulated ice. The boot then must be immediately deflated so that ice does not adhere to the inflated geometry of the boot. This could cause it to fail to deflate or break off ice when the boot is reinflated. The timer, or control unit, can also be made to cycle through the inflation and deflation of all boots periodically, thus relieving the flight crew of repetitive manual activation of the system. The function and capabilities of timers and control units vary. Consult the manufacturer's maintenance information for the performance characteristics of the timer control unit on the aircraft in question. The timer or control unit may be an independent device, or it may be built in as part of another dice system component, such as a central distribution valve. Note, a modern system design may use a pressure switch to signal deflation of the dice boots. When pressure builds in the boots to a preset amount, the switch signals the control valve to close and connect the boots to vacuum. However, this system retains a control unit for automatic cycling of the system at a set time interval, regulators and relief valves. Both the pressure and vacuum developed by an air pump must be regulated for use in the dice boot system. Typical boot inflation air pressure is between 15 and 20 pounds per square inch. Vacuum pressure is set for the requirements of the gyroscopic. Instruments operated by the vacuum side of the air pump. Measured in inches of mercury, normal vacuum pressure, suction, is 4.5 to 5.5 kI. Manifold assembly. In all pneumatic dice boot systems, it is necessary for check valves to be installed to prevent backflow of air in the system. The locations depends on system design. Sometimes the check valve is built into another system component. On twin-engine aircraft, it is common to unite the air supplied from each engine-driven pump to provide redundancy. Check valves are required to guard against backflow should one pump fail. A manifold assemble is commonly used to join both sides of the system. Figure 1528. It contains the required check valves in a single assembly. Inlet filter. The air used in a dice boot system is ambient air drawn in upstream of the gyroscopic instruments on the suction side of the engine-driven air pump. This air must be free of contaminants for use spinning the gyros, as well as for inflation of the dice boots. To ensure clean air, an inlet filter is installed as the air intake point for the system. This filter must be regularly maintained as per manufacturer's instructions. Figure 1529 shows a typical inlet air filter. Figure 1530 shows the relationship of the vacuum regulator and inlet air filter to other system components. Construction and installation of dice boots. Dicer boots are made of soft, pliable rubber or rubberized fabric and contain tubular air cells. The outer ply of the dicer boot is of conductive neoprene to provide resistance to deterioration by the elements and many chemicals. The neoprene also provides a conductive surface to dissipate static electricity charges. These charges, if allowed to accumulate, would eventually discharge through the boot to the metal skin beneath, causing static interference with the radio equipment. Figure 1531. On modern aircraft, the dicer boots are bonded with an adhesive to the leading edge of wing and tail surfaces. The trailing edges of this type boot are tapered to provide a smooth airfoil. Elimination of fairing strips, screws and riv nuts used. Inspection, maintenance and troubleshooting of rubber dicer boot systems. Maintenance on pneumatic desing systems varies with each aircraft model. The instructions of the airframe or system components manufacturer should be followed in all cases. Depending on the aircraft, maintenance usually consists of operational checks, adjustments, troubleshooting, and inspection. Operational checks. An operational check of the system can be made by operating the aircraft engines or by using an external source of air. Most systems are designed with a test plug to permit ground checking the system without operating the engines. When using an external air source, make certain that the air pressure does not exceed the test pressure established for the system. Before turning the desing system on, observe the vacuum-operated instruments. If any of the gauges begin to operate, it is an indication that one or more check valves have failed to close and that reverse flow through the instruments is occurring. Correct the difficulty before continuing the test. If no movement of the instrument pointers occurs, turn on the desing system. With the dicer system controls in their proper positions, check the suction and pressure gauges for proper indications. The pressure gauge fluctuates as the dicer tubes inflate and deflate. A relatively steady reading should be maintained on the vacuum gauge. It should be noted that not all systems use a vacuum gauge. If the operating pressure and vacuum are satisfactory, observe the dicers for actuation. With an observer stationed outside the aircraft, check the inflation sequence to be certain that it agrees with the sequence indicated in the aircraft maintenance manual. Check the timing of the system through several complete cycles. If the cycle time varies more than is allowable, determine the difficulty and correct it. Inflation of the dikers must be rapid to provide efficient desing. Deflation of the boot being observed should be completed before the next inflation cycle. Figure 1532. Adjustments. Examples of adjustments that may be required include adjusting the desing system control cable linkages, adjusting system pressure relief valves, and desing system vacuum suction relief valves. A pressure relief valve acts as a safety device to relieve excess pressure in the event of regulator valve failure. To adjust this valve, operate the aircraft engines and adjust a screw on the valve until the desing pressure gauge indicates the specified pressure at which the valve should relieve. Vacuum relief valves are installed in a system that uses a vacuum pump to maintain constant suction during varying vacuum pump speeds. To adjust a vacuum relief valve, operate the engines. While watching the vacuum suction gauge, an assistant should adjust the suction relief valve adjusting screw to obtain the correct suction specified for the system. Troubleshooting. Not all troubles that occur in a dicer system can be corrected by adjusting system components. Some troubles must be corrected by repair or replacement of system components or by tightening loose connections. Several troubles common to pneumatic desing systems are shown in the left-hand column of the chart in figure 1533. Note the probable causes and the remedy of each trouble listed in the chart. In addition to using troubleshooting charts, operational checks are sometimes necessary to determine the possible cause of trouble. Inspection. During each pre-flight and scheduled inspection, check the dicer boots for cuts, tears, deterioration, punctures, and security. During periodic inspections, go a little further and check dicer components and lines for cracks. If weather cracking of rubber is noted, apply a coating of conductive cement. The cement, in addition to sealing the boots against weather, dissipates static electricity so that it does not puncture the boots by arcing to the metal surfaces. Dice boot maintenance. The life of the dicers can be greatly extended by storing them when they are not needed and by observing these rules when they are in service. Do not drag gasoline hoses over the dicers. Keep dicers free of gasoline, oil, grease, dirt, and other deteriorating substances. Do not lay tools on or lean maintenance equipment against the dicers. Promptly repair or resurface the dicers when abrasion or deterioration is noted. Wrap dice boots in paper or canvas when storing. Electric dice boots. A few modern aircraft are equipped with electric dice boots on wing sections or on the horizontal stabilizer. These boots contain electric heating elements which are bonded to the leading edges, similarly to pneumatic dice boots. When activated, the boots heat up and melt the ice off of leading edge surfaces. The elements are controlled by a sequence timer in a dice controller. Ice detector and ram air temperature probe inputs initiate operation when other flight condition parameters exist. The boot elements turn on and off in paired sections to avoid aerodynamic imbalance. The system is inoperative while the aircraft is on the ground. Figure 1534 illustrated such a system. A benefit of electric dice boots is the conservation of engine bleed air. Current draw is limited to only those periods when dice is required. Propeller dice system. The formation of ice on the propeller leading edges, cuffs and spinner reduces the efficiency of the power plant system. Dice systems using electrical heating elements and systems using chemical deicing fluid are used. Electrothermal propeller device system. Many propellers are deiced by an electrically heated boot on each blade. The boot, firmly cemented in place, receives current from a slip ring and brush assembly on the spinner. Chemical propeller dice. Some aircraft models, especially single-engine GA aircraft, use a chemical deicing system for the propellers. Ice usually appears on the propeller before it forms on the wing. The glycol-based fluid is metered from a tank by a small electrically driven pump through a microfilter to the slinger rings on the prop hub. The propeller system can be a stand-alone system, or it can be part of a chemical wing and stabilizer deicing system such as the TKS sweeping system. Ground deicing of aircraft. The presence of ice on an aircraft may be the result of direct precipitation, formation of frost on integral fuel tanks after prolonged flight at high altitude, or accumulations on the landing gear following taxiing through snow or slush. In accordance with the Federal Aviation Administration (FAA) Advisory Circular AC 12060, the aircraft must be free of all frozen contaminants adhering to the wings, control surfaces, propellers, engine inlets, or other critical surfaces before takeoff. Any deposits of ice, snow, or frost on the external surfaces of an aircraft may drastically affect its performance. This may be due to reduced aerodynamic lift and increased aerodynamic drag resulting from the disturbed airflow over the airfoil surfaces, or it may be due to the weight of the deposit over the whole aircraft. The operation of an aircraft may also be seriously affected by the freezing of moisture in controls, hinges, valves, microswitches, or by the ingestion of ice into the engine, when aircraft are hangared to melt snow or frost. Frost removal. Frost deposits can be removed by placing the aircraft in a warm hangar or by using a frost remover or deicing fluid. These fluids normally contain ethylene glycol and isopropyl alcohol and can be applied either by spray or by hand. It should be applied within 2 hours of flight. Deicing fluids may adversely affect windows or the exterior finish of the aircraft. Only the type of fluid recommended by the aircraft manufacturer should be used. Transport category aircraft are often deiced on the ramp or a dedicated deicing location at the airport. Deicing trucks are used to spray the deicing and/or anti-icing fluid on aircraft surfaces. Figure 1537. Deicing and anti-icing of transport-type aircraft. Deicing fluid. The de-icing fluid must be accepted according to its type for holdover times, aerodynamic performance, and material compatibility. The coloring of these fluids is also standardized. In general, glycol is colorless. Type 1 fluids are orange. Type 2 fluids are white or pale yellow, and Type I4 fluids are green. The color for Type 3 fluid has not yet been determined. When aircraft surfaces are contaminated by frozen moisture, they must be de-iced prior to dispatch. When freezing precipitation exists, and there is a risk of contamination of the surface at the time of dispatch, aircraft surfaces must be anti-iced. If both de-icing and anti-icing are required, the procedure may be performed in 1 or 2 steps. The selection of a 1 or 2 step process depends upon weather conditions, available equipment, available fluids, and the holdover time to be achieved. Holdover time, HOT. Holdover time, HOT, is the estimated time that de-icing, anti-icing fluid prevents the formation of frost or ice and the accumulation of snow on the critical surfaces of an aircraft. HOT begins when the final application of de-icing anti-icing fluid commences and expires when the de-icing anti-icing fluid loses its effectiveness. Figure 1538 shows a holdover timetable for Type 4 fluid. Critical surfaces. Basically, all surfaces that have an aerodynamic, control, sensing, movement or measuring function must be clean. These surfaces cannot necessarily be cleaned and protected in the same conventional de-icing, anti-icing manner as the wings. Some areas require only a cleaning operation, while others need protection against freezing. The procedure of de-icing may also vary according to aircraft limitations. The use of hot air may be required when de-icing, e.g., landing gear or propellers. Figure 1539 shows critical areas on an aircraft that should not be sprayed directly. Some critical elements and procedures that are common for most aircraft are: de-icing anti-icing fluids must not be sprayed directly on wiring harnesses and electrical components, e.g. receptacles, junction boxes, onto brakes, wheels, exhausts, or thrust reversers. De-icing/anti-icing fluid shall not be directed into the orifices of pitot heads, static ports, or directly onto. Figure 15-38. FAA DEIS holdover time guidelines. Airstream direction detectors, probes/angle of attack airflow sensors. All reasonable precautions shall be taken to minimize fluid entry into engines, other intakes, outlets, and control surface cavities. Fluids shall not be directed onto flight deck or cabin windows, as this can cause crazing of acrylics or penetration of the window seals. Any forward area from which fluid can blow back onto windscreens during taxi or subsequent takeoff shall be free of residues prior to departure. If Type 2, 3, or 4 fluids are used, all traces of the fluid on flight deck windows should be removed prior to departure, particular attention being paid to windows fitted with wipers. Landing gear and wheel bays shall be kept free from build-up of slush, ice, or accumulations of blown snow. When removing ice, snow, slush, or frost from aircraft surfaces, care shall be taken to prevent it entering and accumulating in auxiliary intakes or control surface hinge areas, e.g., manually remove snow from wings and stabilizer surfaces forward toward the leading edge, and remove from ailerons and elevators back towards the trailing edge. Ice and snow removal. Probably the most difficult deposit to deal with is deep, wet snow when ambient temperatures are slightly above the freezing point. This type of deposit should be removed with a soft brush or squeegee. Use care to avoid damage to antennas, vents, stall warning devices, vortex generators, etc. that may be concealed by the snow. Light, dry snow in sub-zero temperatures should be blown off whenever possible. The use of hot air is not recommended since this would melt the snow, which would then freeze and require further treatment. Moderate or heavy ice and residual snow deposits should be removed with a de-icing fluid. No attempt should be made to remove ice deposits or break an ice bond by force. After completion of de-icing operations, inspect the aircraft to ensure that its condition is satisfactory for flight. All external surfaces should be examined for signs of residual snow or ice, particularly in the vicinity of control gaps and hinges. Check the drain and pressure sensing ports for obstructions. When it becomes necessary to physically remove a layer of snow, all protrusions and vents should be examined for signs of damage. Control surfaces should be moved to ascertain that they have full and free movement. The landing gear mechanism, doors and bay and wheel brakes should be inspected for snow or ice deposits, and the operation of uplocks and microswitches checked. Snow or ice can enter turbine engine intakes and freeze in the compressor. If the compressor cannot be turned by hand for this reason, hot air should be blown through the engine until the rotating parts are free. Rain control systems. There are several different ways to remove the rain from the windshields. Most aircraft use one or a combination of the following systems: windshield wipers, chemical rain repellent, pneumatic rain removal jet blast, or windshields treated with a hydrophobic surface seal coating. Windshield wiper systems. In an electrical windshield wiper system, the wiper blades are driven by an electric motors that receive power from the aircraft's electrical system. On some aircraft, the pilot's and co-pilot's windshield wipers are operated by separate systems to ensure that clear vision is maintained through one of the windows should one system fail. Each windshield wiper assembly consists of a wiper, wiper arm, and a wiper motor converter. Almost all windshield wiper systems use electrical motors. Some older aircraft might be equipped with hydraulic wiper motors. Figure 1540. Maintenance performed on windshield wiper systems consists of operational checks, adjustments, and troubleshooting. An operational check should be performed whenever a system component is replaced or whenever the system is suspected of not working properly. During the check, make sure that the windshield area covered by the wipers is free of foreign matter and is kept wet with water. Adjustment of a windshield wiper system consists of adjusting the wiper blade tension, the angle at which the blade sweeps across the windshield, and proper parking of the wiper blades. Chemical rain repellent. Water poured onto clean glass spreads out evenly. Even when the glass is held at a steep angle or subjected to air velocity, the glass remains wetted by a thin film of water. However, when glass is treated with certain chemicals, a transparent film is formed that causes the water to behave very much like mercury on glass. The water draws up into beads that cover only a portion of the glass, and the area between beads is dry. The water is readily removed from the glass. This principle lends itself quite naturally to removing rain from aircraft windshields. The high-velocity slipstream continually removes the water beads, leaving a large part of the window dry. A rain repellent system permits application of the chemical repellent by a switch or push button in the flight deck. The proper amount of repellent is applied regardless of how long the switch is held. On some systems, a solenoid valve controlled by a time delay module meters the repellent to a nozzle, which sprays it on the outside of the windshield. 2 such units exist, one each for the forward glass of the pilot and co-pilot. Figure 1541. This system should only be used in very wet conditions. The rain repellent system should not be operated on dry windows because heavy undiluted repellent restricts window visibility. Should the system be operated inadvertently, do not operate the windshield wipers or rain clearing system, as this tends to increase smearing. Also, the rain repellent residues caused by application in dry weather or very light rain can cause staining or minor corrosion of the aircraft skin. To prevent this, any concentrated repellent or residue should be removed by a thorough fresh water rinse at the earliest opportunity. After application, the repellent film slowly deteriorates with continuing rain impingement. This makes periodic reapplication necessary. The length of time between applications depends upon rain intensity, the type of repellent used, and whether windshield wipers are used. Windshield surface seal coating. Some aircraft models use a surface seal coating, also called hydrophobic coating, that is on the outside of the pilot's, co-pilot's windshield. Figure 1542. The word hydrophobic means to repel or not absorb water. The windshield hydrophobic coating is on the external surface of the windows, windshields. The coatings cause raindrops to bead up and roll off, allowing the flight crew to see through the windshield with very little distortion. The hydrophobic windshield coating reduces the need for wipers and gives the flight crew better visibility during heavy rain. Most new aircraft windshields are treated with surface seal coating. The manufacturer's coating process deeply penetrates the windshield surface, providing hydrophobic action for quite some time. When effectiveness declines, products made to be applied in the field are used. These liquid treatments rubbed onto the surface of the windshield maintain the beading action of rainwater. They must be applied periodically or as needed. Pneumatic rain removal systems. Windshield wipers characteristically have two basic problem areas. One is the tendency of the slipstream aerodynamic forces to reduce the wiper blade loading pressure on the window, causing ineffective wiping or streaking. The other is in achieving fast enough wiper oscillation to keep up with high rain impingement rates during heavy rainfalls. As a result, most aircraft wiper systems fail to provide satisfactory vision in heavy rain. The rain removal system shown in Figure 1543 controls windshield icing and removes rain by directing a flow of heated air over the windshield. This heated air serves two purposes. First, the air breaks the raindrops into small particles that are then blown away. Secondly, the air heats the windshield to prevent the moisture from freezing. The air can be supplied by an electric blower or by bleed air. Windshield frost, fog, and ice control systems. In order to keep windshield areas free of ice, frost, and fog, window anti-icing, dicing, and defogging systems are used. These can be electric, pneumatic, or chemical, depending on the type and complexity of the aircraft. A few of these systems are discussed in this section. Electric. High-performance and transport category aircraft windshields are typically made of laminated glass, polycarbonate, or similar ply material. Typically, clear vinyl plies are also included to improve performance characteristics. The laminations create the strength and impact resistance of the windshield assembly. These are critical features for windshields as they are subject to a wide range of temperatures and pressures. They must also withstand the force of a 4-pound bird strike at cruising speed to be certified. The laminated construction facilitates the inclusion of electric heating elements into the glass layers, which are used to keep the windshield clear of ice, frost, and fog. The elements can be in the form of resistance wires, or a transparent conductive material may be used as one of the window plies. To ensure enough heating is applied to the outside of the windshield, heating elements are placed on the inside of the outer glass ply. Windshields are typically bonded together by the application of pressure and heat without the use of cement. Figure 15-44 illustrates the plies in one transport category aircraft windshield. Whether resistance wires or a laminated conductive film is used, aircraft window heat systems have transformers to supply power and feedback mechanisms, such as thermistors, to provide a window heat control unit with information used to keep operating temperature within acceptable limits. Some systems are automatic, while others are controlled by flight deck switches. Separate circuits for pilot and co-pilot are common to ensure visibility in case of a malfunction. Consult the manufacturer's maintenance information for details on the particular window heat system in question. Some windshield heating systems can be operated at 2 heat levels. On these aircraft, normal heating supplied heat to the broadest area of windshield. High heating supplies a higher intensity of heat to a smaller but more essential viewing area. Typically, this window heating system is always on and set in the normal position. Figure 1545 illustrates a simplified windshield heat system of this type. Pneumatic. Some laminated windshields on older aircraft have a space between the plies that allows the flow of hot air to be directed between the glass to keep it warm and fog-free. The source of air is bleed air or conditioned air from the environmental control system. Small aircraft may utilize ducted warm air, which is released to flow over the windshield inner surface to defrost and defog. These systems are similar to those used in automobiles. The source of air could be ambient, defog only, the aircraft's heating system, or a combustion heater. While these pneumatic windshield heat systems are effective for the aircraft on which they are installed, they are not approved for flying into known icing conditions and, as such, are not effective for anti-ice. Large aircraft equipped with pneumatic jet blast rain repellent systems achieve some anti-icing effects from operating this system, although electric windshield heat is usually used. Chemical. As previously mentioned in this chapter, chemical anti-ice systems exist generally for small aircraft. This type of anti-ice is also used on windshields. Whether alone or part of a TKSTM system or similar, the liquid chemical is sprayed through a nozzle onto the outside of the windshield, which prevents ice from forming. The chemical can also dice the windshield of ice that may have already formed. Systems such as these have a fluid reservoir, pump, control valve, filter, and relief valve. Other components may exist. Figure 1546 shows a set of spray tubes for application of chemical anti-ice on an aircraft windshield. Water and waste tank. Ice prevention. Transport-type aircraft have water and waste systems on board, and electrical heaters are often used to prevent the formation of ice in the water lines of these systems. Water lines carry water from the potable tanks to the lavatories and galleys. The wastewater tanks collect the grey water from the galleys and lavatories. Heater blankets, inline heaters, or heater boots are often used to heat the water supply lines, water tank drain hoses, waste drain lines, waste tank rinse fittings, and drain masts. Thermostats in the water lines supply temperature data to the control unit that turns the electrical heaters on and off. When the temperature falls below freezing, the electrical heaters turn on and stay on until the temperature reaches a safe temperature. Figure 1547 is a schematic of a water supply line heater system, and figure 1548 shows the location of the waste water tanks and heater blankets.